Welcome back. So in this video, we are going to continue section 3.1 on some versions of the mean value theorem. So the purpose is to generalize the mean value theorem, but not in the original form. Recall that one corollary of the classical mean value theorem is known as the mean value theorem inequality. So I will call it the mean value theorem version 1.1. It says the following. If I is an open interval of R and F is differentiable on I, and if there exists, and the derivative of F is bounded by a certain constant M, then F is Lipschitz continuous on I with constant M. Okay, this is just a direct consequence of version 1.0. Okay, just take f of x minus f of y equal f prime of cx minus y. Take the absolute value, and f prime of c in absolute value will be less than m. And we get that. So, of course, you can write instead of xa, instead of yb, it doesn't change anything. So, okay. So, in words, the differentiable map with the bounded derivative is Lipschitz continuous. Okay. This is actually the most important application of the mean value theorem, because if we cannot estimate, because c, the number c in version 1.0 is not known. We just know that it exists, but if we cannot estimate it or estimate its size, if you like, the mean value theorem is useless. So and now in this form, we can really generalize the mean value theorem. Okay? And all the versions that I will state should be called mean value theorem inequalities, because they are not equalities, they are really inequalities. Okay. So, and as a consequence of this, we get version 1.2, which is very easy to state, a C1 map is Lipschitz continuous on the compact subset of the interval. Why? Because, as you know, a continuous function, if f prime is continuous because f is C1, f prime is then bounded on the compact sets. Okay, and therefore we can apply version 1.1. Okay, so now we are ready to extend these two versions. Okay, version 3.0. Now, so it's a particular case of the mean value theorem. As now we deal with functions from R to an arbitrary normal space, unlike version 2.0, which dealt with the opposite. So in 2.0, we had maps from a normal space into the real line. Here we have a map from the real line or subset of the real line into an arbitrary normal space. So we assume that f is continuous on the closed interval AB and differentiable inside. So here AB is just an interval. And okay. Then, if there exists a constant, if the derivative of f, which is now actually can be considered as a vector, because the derivative of f at x should be a linear map from R to f, but since we identify linear maps from R to f with elements of f, so f prime of x is just an element in capital F. So if the derivative of f is bounded in norm by some constant, then f of b minus f of a in norm is less or equal than m times b minus a. I don't need to put absolute value because we are assuming that a is strictly less than b. I will not repeat that all the time. But so a and b are, whenever I write ab, I don't consider the case a equal b. It's not interesting. So we always have a strictly less than b. Okay, so this is version 3.0 of the mean value theorem. Okay, the proof is a little bit involved. We'll prove something more, actually. We'll prove that actually it's equivalent. Because if this is true, then we can apply this to any subinterval of the form AX. Okay? And if it's true for every x in A and B, I use continuity. When I let x tend to B, continuity implies that f of b minus f of a is less or equal than mb minus a. Okay, so these two conclusions are equivalent. Okay, so we are going to prove this. So we'll take an element x and a, b strictly inside and prove this. Okay, so continuity will lead to the result. Now, we cannot prove it directly, so we do a typical trick in analysis to prove that C is less than D or equal. We prove that C is less than D plus epsilon for every epsilon. Okay, so this is really a typical proof in analysis. So to prove this, we prove actually that the norm of f of x minus f of a is less than m plus epsilon x minus a plus epsilon for every epsilon. If this is true for every epsilon, then letting epsilon tend to 0 will give me the result. Okay, because everything is fixed here. So the epsilon is independent on m and a and x. So now how to prove that? We reason by contradiction. So we give a positive number epsilon, so we fix it in this discussion, and we consider the set U where this inequality of all points or all numbers x between a and b such where this inequality is not satisfied. Okay, now if we prove that U is empty, then this would be proved, and therefore this will be proved, and therefore this will be proved. So this is our strategy. So we have to prove that this set U is empty. So we reason by contradiction. Okay. Now, if we set phi of x to be norm of f of x minus f of a minus m plus epsilon x minus a minus epsilon, then it's very easy, since f is continuous and the norm is continuous, we see easily that phi is a continuous map. So U is actually the inverse image under a continuous map of the open interval 0 infinity. So U is an open set. Okay, actually, it's the intersection of two open sets. Okay, so suppose by contradiction that U is not empty. Then, since by definition any element in U is bounded from below by A, then U is bounded from below. And as you know, any non-empty set which is bounded from below has an infimum. So let this infimum be C. So C is bigger or equal than A because A is the lower bound. However, C cannot be equal to A. Why? Because if C equal A, then, and C is the infimum of U, then by a fundamental property of the infimum, there is a sequence xn in U that converges to C, which is the same as A. Since xn is in U, then phi of xn is positive. But since phi is continuous, phi of xn converges to phi of A. So at the limit, I get phi of A is bigger or equal than 0. However, if you compute phi of A, you'll get 0 here, and minus epsilon. And this is a contradiction. So C cannot be equal to A. Second claim, C is not in U. And this is a particular case of a general fact in the topology of R, that the infimum, we know that the infimum of a subset of R belongs to the closure of the set. But actually, it cannot belong to the interior. So it actually belongs to the boundary. Okay? So the infimum of an open set cannot be in the set. Okay? This is very general. You check that. I never stated that explicitly in second year, but because this is something that you can easily deduce from the definition. Okay, so you can reason by contradiction. Suppose that C is in U, what happens? Okay, so C is not in U, and third thing that I can prove is that C cannot be equal to B. Okay, why not? So actually C is strictly less than B. So why this is true? Take an since U is not empty, consider an element x0 in U. Then by definition x0 is an AB in the open interval AB. And since x0 is in U, it's bigger than the infimum of U. So x0 is bigger or equal than C. But B is strictly bigger than x0. So C is strictly less than B. Okay. Now we continue. Since C is inside the open interval AB, the assumption of the theorem tells me that the norm of the derivative at C of f is less or equal than m. On the other hand, by definition, or it follows from the definition, because here we are dealing with a real variable. Okay, so x is a real number, c is a real number. So if you go back to the definition of f prime that we stated, it's equivalent to saying that, and this is actually the familiar definition of a derivative, but we modified it a little bit in order to generalize it. But when the variable is real, this is really equivalent to the definition of f prime of c. Okay, it's the limit of Newton's ratio as the denominator tends to 0. And so, in particular, since the norm is continuous, the norm of this ratio tends to, there's an error here, this should be the norm of f prime. Okay? Because norms are continuous. So, in particular, the difference between norm of f prime c and this ratio is between minus epsilon and epsilon. So, in particular, the difference is greater than minus epsilon. Okay. So, of course, for x sufficiently close to c. Okay. This is the definition of limit. Okay, and now, since f prime of c is less, a norm is less than m, then I get, okay, but before doing that, by a property of the infimum, any interval of the form c plus delta meets u. Okay, this translates the fact that c plus delta is not a lower bound. So there is an element in u which is less than c plus delta, and of course it will be greater than or equal than c. So choose an element x in this intersection, an element x in u which is less strictly than c plus delta. And since c is not in u, then x cannot be equal to c. Right? So x is strictly bigger than c. Okay, so we choose that x. And now I apply this inequality because now x satisfies this. Okay, x is now between c and c plus delta. So for this x, we have this inequality. And now I combine this inequality with this inequality, and I get m is greater than the norm of this ratio minus epsilon. So if I add epsilon and multiply by x minus c, which is positive, okay, this is once again a real number, not a vector. F of x is a vector, but x and c are numbers. So when I multiply by x minus c, I get that. But since we proved that c is not in u, then c satisfies this inequality because u is the set of points that do not satisfy this inequality. And now I just apply the triangular inequality. If I add these two, I get f of x minus f of a in norm is less than this quantity plus this quantity. So I factor by m plus epsilon, and I get x minus c plus c minus a, which is x minus a, and the epsilon doesn't change. Okay, what does this mean? This means that x satisfies this inequality, and therefore is not in u, and this is the contradiction. Okay, therefore, my assumption that u is not empty was wrong. So u is empty, and therefore we have the inequality. Okay, so this concludes the proof of version 3.0. Now let us deduce, as expected, some consequences. Version 3.1. So now we move to a general function between Banach spaces or norm spaces, because so far we never needed the assumption of completeness. We'll need it later. Okay, so we can work between arbitrary norm spaces. Okay, so if the straight line segment AB is contained in U, and the derivative of f is bounded by a constant, then the norm of f of b minus f of a is less than this constant times b minus a. This is the mean value inequality. So the proof is just a copy of the proof of version 2.0, if you like. So same strategy. So we consider the the parameterization of the straight line segment AB, and we introduced the new function G, which is the composition of these two maps. And now we get G is now a map from 0, 1 into F. So we can apply the version 3.0. Okay. So, and then we continue as in the proof of 2.0. So you can do it actually. It's very easy. So same thing. Okay, we deduced 2.0 from 1.0. Here we are deducing 3.1 from 3.0. And the same arguments actually show another version similar to version 2.2, I think, or 2.1. If F is continuous on the closure of an open set and differentiable on that set, and if the open straight line segment joining A to B is contained in U, and the derivative is bounded inside the interval, inside the straight line segment, then same conclusion. Okay, so here the same remark as we did in the previous video. Okay, we cannot deduce 3.1 from 3.2, but the same proof shows both actually are true. Okay, there is a slight, very nuanced, a very delicate difference between the two assumptions that I explained on a figure. Okay, in version 3.2, A and B could be on the boundary of U, so F need not be differentiable at B or A. However, here in version 3.1, F is differentiable at A and at B. Okay, and it's we don't need F to be C1 actually. So, right. So it's possible that F prime of X as X tends to B go to infinity. Okay, so, but here we didn't assume that F is continuous on a bigger set. Okay, so there are independent versions. Okay, and as a corollary of this, we get this following form, 3.3. If U is open and convex and F is differentiable on U, and the derivative is bounded, then F is Lipschitz continuous. Okay, so just apply version 3.1, because now, of course, you can put F of B minus F of A less than MB minus A, same thing. Okay, but when I write X, Y, it tells you that they are really variable here. Okay, so this is Lipschitz continuity. Okay, so just apply 3.1 to this case. Okay. So same thing, and the last version, 3.4, states, similar to a previous version, if U is open and convex, and U is of class C1, then F is Lipschitz continuous, not necessarily on the whole of U, because this need not be the case, but it's Lipschitz continuous on the compact subset of U, which means that when I restrict F to any compact subset of U, I get a Lipschitz condition with constant depending on the compact set. Okay, so the constant may vary from compact set to compact set. Okay, so it's not uniform. Okay, so this concludes the material of section 3.1. And before I leave you, I will give you a challenging exercise. It's completely optional, so you don't need to, if you are not interested. This is only for the really interested students who want to dig deeper in analysis and want to become analysts later. So if we have a map F defined on any set of a norm space and taking value in another norm space, so we don't need the assumption that U is open here. It's not, it's irrelevant. We say that F is locally Lipschitz continuous, or just locally Lipschitz, or satisfies locally a Lipschitz condition if every point X in U has a neighborhood on which F is Lipschitz continuous. Okay, so here again, the Lipschitz constant depends on X. Okay, and now consider the following two conditions. F is locally Lipschitz continuous, condition 1. Condition 2, F is Lipschitz continuous on compact subsets of U that we had in the last corollary. Now, these are the questions. Show that 2 implies 1 if the dimension of E is finite. First question. Second question, give an example of a locally Lipschitz continuous function, which is not globally Lipschitz. This is not difficult. Actually, these A and B are straightforward. C and D, we have to show that 1 implies that F is continuous. So the local Lipschitz condition implies continuity, and the Lipschitz continuity on compact sets also implies continuity. Okay, not terribly difficult, but not trivial. And now, less trivial, challenging. 1 implies 2. And the most challenging question, what happens to the implication 2 implies 1 if the dimension of E is infinite? So this concludes section 3.1. Thank you for your attention and see you in the next video.